All right. Hello, everyone. Welcome to another review session of Fundamentals of Heat and Mass Transfer. Today, I'll be talking about Chapter 13 in in the radiation sections. All right. So, Chapter 13 is all about view factors, and view factors are they're essentially here in Section 13.1 it says that the concept of a view factor, also called a configuration or shape factor. The view factor, Fij, is defined as the fraction of the radiation leaving surface I that is intercepted by surface J. So view factors are purely a geometric term, right? And it's essentially how much radiation leaves surface 1 and is intercepted by surface 2. Okay, so the big difference between chapter 12 and chapter 13, if you remember from the review video from chapter 12, that was all about when the solid angle is much less than 1. Chapter 13, however, is always true. So I guess to some extent, when in doubt, use chapter 13. The biggest difficulty with using chapter 13 is that you have to have some sort of tabulated value, right? So you'll see let me look up that table. For example, you'll look in table 13.1, right? And it has a bunch of different cases where you can compute a view factor. However, this is somewhat of a complication because this is not a generalized case, right? So you have some double integral definitions that you can use if you have enough information to compute those double integrals. That's not really a focus of this class though, so I wouldn't worry too much about that. So the one of the big concepts then is if you have some sort of complicated surface or geometry, it's much easier to use chapter 12 than it is to use chapter 13. But if you have some sort of tabulated value or some tabulated case, such as table 13.1, if your problem matches one of those cases, then 13 is always true, independent of what the solid angle is. Okay, so um, this is a list of topics that we're going to talk about today. So we talked about what a view factor is. So it's the amount of radiation leaving surface 1 and hits surface 2, right? It can always be used as long as you have a view factor or configuration factor. If not, you have to create your own using the cross strings method or the view factor integral method. Okay, so I think let's start with the reciprocity rule. So this is equation 13.3. It's important to note that all these equation and formula numbers are as denoted by the 7th edition of the Bergman, Lavine, Incropera, and Dewitt book. All right. Okay, so the reciprocity rule this is a very big concept for chapter 13. So as we see in equation 13.3, we have AI Fij is equal to AJ FJI. Okay, so so I's and J's are just the indices, right? So if I was your surface 1 and J was your surface 2, this is the area of 1 times the view factor, which is it's the amount of radiation leaving surface 1 intercepted by surface 2 is equal to A subscript 2 times the amount of radiation leaving surface 2 and intercepted by surface 1. So this rule is actually very important in finding view factors, especially if you have some sort of complicated enclosure involving multiple surfaces, because a lot of times, for example, it might be trivial depending on your case. It might be trivial to find F34, but not so trivial to find F43, right? So let me maybe write that. So F34 might be easy, and F43 might be not so easy. However, if given enough information about the areas, you can use the reciprocity rule, and then F43 becomes pretty trivial. Okay, so I think that'll become more obvious as you do example problems and such, but reciprocity is a big thing, especially for enclosures. Okay, the other thing is this equation 13.4 that states that the summation of j equal from indice j equals 1 to n indices fi j is equal to 1. All right, so what does that mean? Let me draw out some sort of example here. So let's say we have this, well, we could say we have a box enclosure, right? So this is surface 1, this is surface 2, this is surface 3, and this is surface 4. So let me start this, and we're going to call this the summation rule because it's just a summation. All right, so what does this mean? This means that F11 plus F12 plus F13 plus F14 is equal to 1. So the summation rule is pretty handy because you can start, maybe you have some information and you're able to find F13 and F11 and F14, but now you need to find F12. Well, instead of doing a bunch of, the double integrals or the cross strings method or something, you can use the summation rule in order to find F1 to 2, right? So generally when you start with the summation rule, what I do is I start with this first term and I ask myself, can surface 1 see itself? Right, so what do I mean by that? So let's say we have some sort of concave surface, right? And you have some amount of radiation leaving in an arbitrary direction, okay? What you have to ask yourself, is it possible that some radiation leaving point 1 could be intercepted, maybe I call this point A, I apologize for that, could be intercepted by point B. And all you have to ask yourself is it possible that radiation leaving A is, and maybe I can say directly intercepted by point B? And like I say, it's arbitrary, right? So you could have some going here or here. This could as well be surface C, right? But really, you just have to ask yourself if there is a random angle that this radiation from point A is emitted, is it possible that the same surface receives that radiation, right? So this happens with concave surfaces, right? So if it's not a concave surface, it does not see itself. So you need to ask yourself, does the surface 1 see itself, right? So obviously, if you have a plane, right? Oh, okay, here we go. So obviously, if you have a plane, it doesn't matter what direction the radiation is emitted. It will never, ever be directly intercepted by the same surface. However, if you were to say have some sort of cylinder, so we have a hollow cylinder here, right? And the inside of that, hollow cylinder is surface 1, then that is concave. And if we ask ourselves, does the surface 1 see itself? Okay, it is concave, so anything that's concave will see itself. So by concavity, you can say it will see itself, but then you can ask your question, does the surface see itself? So draw an arbitrary point in an arbitrary direction and some radiation in an arbitrary direction, right? Or A and B. Is it possible that A hits B? And in this case, there is an arbitrary, or there is a arbitrary or random case where A is intercepted by B, and so yes, it does see itself in this case. Okay, so let's go back to our example. We essentially just had a square box where we had 1, 2, and I believe 3. Let's double check that. Yep, and 4. Okay, and this is a box, right? So surface 1 is a plane. So can surface 1 see itself? No, because it's a plane. So the surface will never, ever directly receive radiation emitted from itself. Okay, and then we continue with the summation rule. And as you can see, we have already simplified to some extent this summation rule. All right, now you should be, in an actual problem, you'd be given more information so that you could actually calculate F12, F13, F14, right? So for example, here I would start looking for cases, right? So F1 to 2 is 2 planes perpendicular to each other. F13 are parallel planes. And F14 is also perpendicular planes, right? So at this point, I would go to 13.1 and I would say, oh, parallel planes, at least parallel planes with midlines connected with perpendicular, right? Which that case is outlined in the table, right? So this is case number 1 in table 13.1. Okay, then I would start looking through, okay, inclined parallel plates of equal width and a common edge. Okay, they're not necessarily, well, let's see, equal width. Yeah, so you could use case 2 from table 13.1. Oh, sorry, you'd actually use case 3 because that is perpendicular plates with a common edge. I apologize, my pen must be running out of batteries because it's acting up. You can also use figure 13.4 and figure 13.6. Depending on what information you're given, which one's easier to use, right? So view factors, the actual calculation using the integrals and cross-string method and Monte Carlo simulations and all that, that is actually a little bit more complicated, but that's not the focus of the class. The focus of the class is more of, do you understand what a view factor is, when to use it, how to use it, right? So reciprocity, summation, and then using the tables and the figures are good. Oh, the other thing is, for example, this would be figure 13.7, right? In the 7th edition, and essentially you have a case where you have perpendicular plates, but they're not of equal width, right? So as in figure 13.7, what you can do is you can just say, let's see, well, maybe that notation won't be good. Okay, so what you would do is you would split this up so that you can have some cases where they are where they do meet conditions in the table, right? So if I were given something like this, I would start splitting it so that I could use case 3, right? So the dotted line represents essentially an imaginary surface, right? And I would split this. Sorry, that would be 1, surface 1. Oh, my pen. Surface 2, surface 3, and surface 4, right? So what you could do is you would find so A1, 4, so this whole surface, F, and then it would be 1, 4, 2, 2, 3 is also equal to A 2, 3, F 2, 3, 1, 4, right? And let's say we are looking, I'm sorry, let's see, let's say, because I should define my find, right? My find may be F 1, 2, 2, 3. All right, so I can find F1, 4 to 2, 3 pretty easily, right? But now what you can do is you can start subtracting, right? So F1, 2, 2, 3 would be equal to all of the ways that, because 4, surface 4 is the imaginary surface, right? So, you know, it's this green surface, this is imaginary. So this one would be the F 1, 4 to 2, 3, which would be pretty trivial to find. Use tables. And then we would minus the view factor F 4 to 2 minus the view factor F 4 to 3, which should be, it should not be too hard to find using the tables. Okay. All right. So let's just take a second and recap before we move on to, so what is a view factor? It's the geometrical representation of how much radiation leaves surface 1 and is intercepted by surface 2. When can it be used? It can always be used as long as you can find it, right? And like I said, actual finding it using the math with the double integrals isn't the focus of the class, but being able to use the tabulated values in the figures is definitely a part of it. Reciprocity rule, right? That's where, you know, for example, A1F 1, 2 is equal to just the reverse of that, A2F 2, 1. Okay, enclosures, right? This is where we said the summation, oh, that's not a summation sign, I apologize. Summation of j to n of a I f I j is equal to 1, right? So that was the f11 plus f12 plus f13 plus f14 is equal to 1. And like I gave you an example of a 4-surface enclosure, but it could be any number. It could be a 2-surface enclosure. It could be in you know, hundreds of surfaces, right? And then we say, does this surface see itself? Yes, and so in order to answer the question, does the surface see itself? You simply just have to ask, is it concave, right? Because if it's concave, it will see itself. If it's not concave, it will not see itself. If it does see itself, you just have to continue with this view factor algebra. So using this first one, reciprocity, this second one, summation, that's the view factor algebra, right? So then you'd have to um, probably use the tables, the figures, along with reciprocity in order to find out what these others are, including F11 if it sees itself, right? Okay, so yeah, when can it be used? Let's remember that. So chapter 12 is really useful if the solid angle is much less than 1 and you do not have a tabulated view factor, right? Again, chapter 13 can always be used, but it's important to have the actual view factor, and it has to be, the math has to be doable in order to compute the view factor, right? The other thing is that this subject of enclosures that we see here, right? So if it's an enclosure, chapter 13 is the way to go, because if it's an enclosure, the solid angle is not much less than 1, right? So if you have some sort of enclosure, then you use the summation rule along with reciprocity, and you can also use radiation resistance networks. All right, so let's go to equation 13.19. Okay, so in radiation resistance networks, right, so you essentially, if you remember from chapter 12, we use things like emissivity to say, hey, this is how close a real surface approximates being a black body. So using these radiation resistance networks, right, it's the same concept as we used in chapter 3 for thermal resistance. So if you want to know the driving potential, temperature difference, if you want to know the resistance, or if you want to know the total heat transfer rate, these are really useful. Okay, so for radiation, it's a little bit different, right? First off, what we start with is equation 13.19 in the 7th edition, right? And this says that the heat rate is equal to the emissive power of a black body minus the radiosity over 1 minus the emissivity divided by emissivity times the area. All right, so let's draw this out. So essentially with radiation, instead of having temperature nodes, you have emissive power and radiosity nodes. But it's the same idea. Okay, where this is Ji and this is EBI. Right, so let's think about this. What's the emissive power of a black body? It's sigma Ts to the 4th, right? So it's still, this is still being driven by a temperature difference. But what we're saying is we have something that should act like a black body, and then we have this is essentially like the real surface properties, right? And then the radiosity of that surface. So it's the exact same idea as I just spoke about, where the emissivity tells us how much the real surface approximates to a black body, right? So you start with a black body, you add the real surface properties, essentially, right? And then that gives you the radiosity of the real surface, right? So this is radiosity of real surface. And then that radiosity hits another surface, which would be, in this case, I might say JJ. Actually, let me give myself some more room, where it would then go to black body J, where this is 1 minus I, right? And then this one would be A I F I J. Yep. Okay. Yeah. So let's think about what you do is you draw out your system, right? So for example, my system is essentially this enclosure that's a box, right? 1, 2, 3, 4. So what are all the ways? So first off, let's make surface 1. So to make surface 1, we start with the black body, and then we get to the radiosity, and we say that's 1 minus the emissivity of 1 divided by the emissivity of 1, A1. Okay, and then what are the different ways? Well, it can go to 4. So I'd have J4 here. It can go to 3. So I'd have J3 there. Whoops. And it can go to surface 2, right? And then I need to finish this circuit because I've got these going to the radiosities of each, but just like we started with the black body, we essentially do the same thing, except this time we're ending with the black body. So this would be EB4. EB3, EB2, 1 minus emissivity for A4, 73, epsilon, 3A3, 1 minus E2, E2, A2. Right, and this one would be A1F 1 to 4. Or sorry, that's 1 over that, right? I believe that's 1 over that value. Oh no, I do have that correct. Okay. Yeah, so this one would be A1F 1 to 4, A1F 1 to 3, A1F 1 to 2. Okay, so you can also use these radiation resistance networks to find your total view factors, or your view factors for, 1 to 4, 1 to 3, 1 to 2. You could use them to find the emissivities, the total heat rate, the radiosities, the emissive power of the black bodies, right? You just have to remember, again, it's the energy balance of what comes in is equal to what goes out, assuming steady state. Okay. All right. So essentially, again, with the enclosures, with the radiation resistance networks, start with a black body, add a resistance to make it a real surface, add a resistance to add a resistance from surface to surface, and then again, make it go from surface to ideal. So ideal to surface, surface, yeah, so maybe if I do it in red, right, where this is ideal, surface, surface, then ideal. I hope that makes sense. Let's see what else besides that. Let's see, did we use, just double check, did we use 1321? Yes, we essentially used 1321 by using the radiation network. 13, that might be a typo, 13, oh, figure 1310. Okay, let me just double check on that. Yep, we essentially made 1310. And then, if you want some more practice, you can do example 13.4. Table 13.3, special diffuse gray, 2 surface enclosures. It's basically what we've done. You should be able to derive those. Talked about table 13.1, figures 13.4 through 13.7 we talked about. And then the other big thing is to relate this to heat transfer rate using view factors, right? So, I mean, we can use the radiation resistance networks and relate that to heat rate because we've done similar things using Ohm's law. But let's talk about equation 1313 and 1314, it looks like in the 7th edition. Okay, yep. All right, so that would be Qij is equal to AIFij sigma Ti to the 4th minus Tj to the 4th. This is just simply how you relate view factor to heat rate, right? So this equation is really important, right? Because, for example, let's say you have some sort of detector, and here we have some sort of emitter, right? This is a common problem, and we'd want to know what the signal of the detector is, right? So you say the signal of the detector is proportional to the Q radiation in, right? Because if you draw your system here, right, we have some Q radiation in. Technically, for a detector, we'd have some power going out, and we'd have an emission term, right? But we say the signal is proportional to the radiation coming in, which makes sense, right? Because if there's more radiation coming in, the signal should get, the quantity of the signal should get larger and larger, and vice versa, right? So we say, all right, so what? So leaving surface I, arriving at surface J. So I'm going to say I is the emitter, J is the detector. You'd say that Q radiation is equal to the A of the emitter times the fraction of radiation leaving emitter going to received by the detector times sigma, and then times temperature of the emitter minus temperature of the detector, both raised to the 4th, right? And so in this case, if you had 2 circular disks, you could use the table or figures to find FED if 2 coaxial disks, right? So that's just an example, right? And so then you'd be able to solve that problem pretty easily now, given some geometric information about the emitter and the detector. Okay. The other thing is, one thing I forgot is when you're finding view factors, right? Like, let's say you're given this curved surface, right? And it's surface 1, right? And the question is, you know, let's say this is some sort of channel. So let's find the radiation leaving the channel. What you want to do is you want to draw initially, right? So let me kind of draw this better. You have this channel and you want to find the radiation leaving the channel. So what do? Draw, and in red, I'm drawing this plane surface that is actually an imaginary surface. And why do I do that? It's because I can make it an enclosure by doing that, right? Because now I have two surfaces, right? Because then you can say F11 plus F12 is equal to 1 using the reciprocity rule, right? And from here, you would look in tables, figures, or given other geometric givens in the problem, you'd be able to find these view factors. Okay, so same thing, you know, if you have some sort of cylinder and it's above some sort of plane, right? This is not an enclosure, but you could make it an enclosure by drawing two imaginary surfaces, right? So now you have 1, 2, 3, and 4. Or likewise, if it was in the middle, right, you could cut this down and call it symmetric. Okay, so again, let's go back and recap just a little bit. View factor, what is leaving surface 1 received by surface 2. It can always be used as long as you can do the math to find it. Reciprocity rule, right? So we went over that. A1F12 is equal to A2F, just the reverse of that, A2F21. So what's received by surface 1, or sorry, so like this first part is like saying what's received by surface 2 is the same as, so what, maybe explain it a little better. How surface 2 views 1 is the same of how surface 1 views 2 as long as you multiply by the areas. All right, so I hope that works. Summation, been over that, right? That F11 plus F12 plus all the way to F1n is equal to 1. Always start by asking yourself if the surface sees itself. If it is concave, you have to do some algebra to find that. If it's not concave, then you can just cross it out and call it 0, right? The radiation resistance networks, right? So that was right here. Start with an ideal surface, add the surface properties and make it a real surface. Have some exchange between a real surface and a real surface, and just use the definition of the view factor for that. And then again, go from a real surface to a ideal surface. And then these tend to be a little bit more complicated than the radiation stuff, or sorry, the resistance stuff we've solved in the past, but it's still doable. Definitely using Ohm's law. What, you know, the current coming into any node is the same as the current leaving each node. In order to find view factors of specific view factors of enclosure of problems, it's incredibly helpful to make it an enclosure. You know, with this example I did with the red surface, where I drew an imaginary surface and it made it an enclosure, right? Because this summation rule right here, that I'm going to underline in red, this is only valid for an enclosure. And then I would say, so if needed, make it an enclosure by drawing an imaginary surface and solving. Okay, so radiation resistance networks. We talked about two surface enclosures, tables, figures, and then the big idea too is this black body radiation exchange, which I will also underline in red, right? Which is here, which is how you relate a view factor to the total heat transfer rate, right? So now, just as a real quick example, in video about chapter 12, we had the sun and it was incident on some rocket, right? So let's see, sorry. Right, with some exhaust coming out. And we were interested, so let's see, so review chapter 12, find temperature of the rocket wall, right? But now we would be interested in how much heat transfer happens from the wall to a cryogenic tank, right? So this might be rocket wall. And you have a cryogenic tank here, right? So this is LOX is what they call it, which is equal to, it's the same thing as liquid O2. Okay, so what would you do? So this one was chapter 12. We found the temperature of the wall. But now what I would do here is first I would say, we're interested in the heat transfer rate to the tank, right? So I would say, what is the solid angle from the tank to the wall? And then I would just say it's obviously large, right? Because they're the same size. So do not use chapter 12, right? So you have to use chapter 13. So we have some heat transfer rate. Now we could call this 1 and call this one 2. We have some heat transfer from 1 to 2, right? So there's a couple ways you could go about doing this depending on how you wanted to use your approximations, right? So you could say, use the heat transfer rate 1 to 2 for case 1, parallel plates connected with a midline, with connected midline, right? So case 1, table 13.1. Another option, remember, is we said to draw an enclosure, right? So you would draw two surfaces here where you'd call them like 3 and 4. And then you'd start by saying F11 plus F12 plus F13 plus F14 is equal to 1. Then remember the next step was to ask yourself, does it see itself? Nope. Right? And so given enough information, you should be able to find these using tables and figures. Using tables, figures, so using tables, figures, and reciprocity. Those are the 3 keys to finding view factors for an enclosure, right? So obviously you would be able to find F1 to 2, right? And then given the right information about surfaces, about the width of 3 and 4, you would also be able to find those. And then you would want to, so then we know that there's sum coming from f1 to 2. Okay, so there's f, there's some amount leaving 1, arriving at surface 2. There's some amount leaving surface 3, arriving at 2, and there's some amount leaving surface 4 and arriving at 2. Right? And so you could sum all of these in order to get the total heat transfer rate to the tank as an enclosure. Okay, so again, just to finish up the video, I think we've hit the nail on the head enough with what is a view factor, when it can be used, reciprocity rule. If it's an enclosure, just basically always use chapter 13, use the summation rule, the reciprocity rule. If it helps, use radiation resistance networks. Likewise, what we did here, you could also draw a radiation resistance network if that's an approach that you wanted to go with. Really, it's somewhat hard to say, especially for these things in chapter 13, which approach to use. You kind of just have to try them out and figure out which one works for you. There was also this case that I forgot to recap on where there was a case that was not explicitly stated in the tables, but you can add imaginary surfaces, use a case in the book, and then subtract that imaginary surface, right? If it's concave, it sees itself, and then just this big red equation, right? So always use a view factor to in some way relate to the heat transfer rate or temperature, right? Because that's usually what we're trying to find, right? So we can use enclosures, we can use this red box equation. In doing enclosures, we can draw imaginary surfaces. We can use view factor algebra for the reciprocity rule, the summation rule, and we can also use the radiation resistance networks. I hope this video was helpful. These are just kind of the big things that I think are useful out of chapter 13. Yeah, so if you have any comments, any suggestions on how to improve the video or future review videos, yeah, just drop those comments down there and I'll try and improve some videos for the future. Hope this helps. Thank you so much for listening and hope you do well on your exam.